Morning, everyone. So in yesterday's class, we ended off with an esterification reaction, how basically we can combine an alcohol and a carboxylic acid, end up releasing off of water. We call that reaction a condensation reaction, and then we basically glued the two halves together. So I just pulled a couple pictures out of my organic textbook here. You see we're starting here with a carboxylic acid, it a characteristic COOH group here. This one here is acid catalyzed, so you see that the O actually attacks the H plus first. You see a little bit of movement of these electrons here. Double-headed arrows refer to two electrons doing the moving. Then comes our alcohol grouping here. The O group also attacks the carbonyl, that C portion of it here. Then I have the two odd oxygens there. We have what's referred to as a hydride shift, when the hydrogen sort of jumps from one to the other. Again, we draw arrows from where the electrons start to where they're sort of being picked up. The hydrogen ends up going to the opposite side, and that's actually how we actually release off the water. We end up releasing off the H+. The catalyst basically picks up the acid again, and therefore we end up forming an ester. Remember, this reaction here is reversible, so this totally could go backwards as well, and you can use the chatelier to actually shift it one way or the opposite way here. You also see sort of another diagram of that process of esterification, again using acid catalyzed. I couldn't really find an amidation mechanism, but just to give you a sense of how complicated the mechanism looks like here, we have again a carboxylic acid. I have this catalyst here, and eventually what's going to happen here is our amine is going to add as ammonia, and then basically it then adds on the ending, and now it ends up forming an amide. So those ones you definitely don't need to know the mechanisms for. I just wanted you to just have it in your notes, so in case you were wondering, you can see it there. With that in mind here, we're going to just, again, just do a quick recap of that mind map. So far we've seen most of the connections that we're going to be doing in this chapter here. Today we're going to switch over to introduce benzene and some sort of special reactions that it undergoes, and then tomorrow we'll finish off with a little bit of reduction. So let's just start off here trying to practice our mind map. Hopefully this isn't foreign to you now. So we're going to start off here. We began with our alkane family. Alkanes are hydrocarbons. They're fairly unreactive because their single bonds are very, very strong. Alkanes undergo combustion reactions. So in the presence of O2, I'm going to put Cp again for combustion products. If you assume complete combustion, that would be CO2 and water. If it's partial or incomplete combustion, you end up getting carbon monoxide or unburned carbon, which ends up looking coming off as soot. So it's a very dark, smoky flame. Alkanes can also react with chlorines or bromines. That is a substitution reaction. But this one here has to have a energetic form of light here, UV, in order to then make it a halogenoalkane, or what's referred to as an alkyl halide. These interconnections are going to be important for tomorrow's lesson. Essentially, what we're going to do is we're going to have some target molecule in mind, thinking about the functionalities that are on that molecule. We're going to try to come up with a way to actually create that from precursor molecules. Let's just switch over to look at alkenes. Alkenes have a double bond, but you do need to specify it's a double bond between carbons. For example, aldehydes have double bonds to oxygen. That's not an alkene. It is a double bond. We're only going to deal with having one double bond, although technically alkenes could have any number of them. Every time a single bond converts itself into a double bond, it actually loses two hydrogens, and we pick up what's referred to as 1 degree of unsaturation. We can convert alkenes to alkanes, no problem here. This is called hydrogenation. I'm going to end up adding a hydrogen. This one here needed a nickel catalyst or palladium or platinum as a catalyst, slightly hotter than room temperature. We usually say 150. This would also convert alkynes first into alkenes and then alkanes. So hydrogenation can happen twice there, but we focus mainly on these alkenes here. I can convert alkenes over into my halogenoalkanes by adding an HX across a double bond. This one here, we have this occurs at room temperature. So this one gave us a really nice a test for whether we have multiple bonds here, because if you add a sort of bromine style compound, actually it's more so this one here, if I add let's say an X2 also at room temperature, if you add a bromine compound, alkanes will only react with pulses of UV light, whereas Br2 here for to become a dihalogen alkane, this one can occur at room temperature. We usually use bromine because its color starts off as like a reddish brown liquid. So if the liquid reacts, the color actually disappears. It's much more obvious, whereas in the alkane case, it would only occur if there was UV light present. So this one here ends up forming a dihalogen alkane. It's an alkane with two dihalogenoalkane. Technically here, this alkane substitution through that free radical mechanism, if it happened more than once, you could also end up having a dihalogen alkane. So sometimes they do draw this arrow over that way as well, but under the same reacting conditions. Sorry, what's going on here? Dihalogenoalkane. Okay. Alkanes can also add to themselves. So alkanes plus other alkenes can alkenes and other alkenes can end up forming polymers. Basically, we have a small unit called a monomer, and basically it attacks itself over and over again n times and ends up stringing together a really, really long compound. That's a polymer here. Again, probably the most important one that we did here. Again, important to note that this one here is in equilibrium, so this one could go either way. This one here does require concentrated sulfuric acid as a catalyst. A little bit of heat treatment as well, but what we're going to do is we're going to add water. Right? So as I add a water, you can think of adding an H and OH across the double bond here. Remember, we had our Markovnikov's rule here. If your alkene is asymmetric and it already had one carbon with more hydrogens, the hydrogen on these things that I'm adding, whether it be water or a halide, it gets added to the one that already has more hydrogens. Therefore, the carbocation that gets created is more highly substituted. It's going to be more stabilized by those inductive effects. So this one here ends up forming our alcohols. At this point here, we see that these guys here all undergo combustion reactions. So you can burn them, you can burn alkenes, you can burn alcohols and all that. Okay, alcohols we found were the most reduced form. In the presence of an oxidizing agent, it can slowly add more oxygens, or losing hydrogens is another way to see oxidation in this chapter here. Usually the oxidizing agent that we use is acidified dichromate, so H plus Cr2O7 minus 2, that was an oxidizing agent. But depending on sort of what degree your alcohol was, a couple of things could happen. You can have a primary alcohol, a secondary alcohol, a tertiary alcohol. Tertiaries are the easiest ones here. These ones have no reaction. Because they're already tertiary, it's carbon bonded to 3 other carbons. You would actually need to break the carbon structure, which isn't all that easy as we saw for the alkene, low reactivity. For a secondary one here, a carbon that's bonded already to 2 carbons, you can lose a C and H bond and end up forming a carbonyl. So that ends up forming a ketone. This one here, again, you do want to note that the triangle here means heat treatment here. This one could undergo via distillation as well, but we saw distillation was really important just for trying to stop the primary alcohol from getting all the way over to carboxylic acid. So I usually just put reflux. For the primary, as I just alluded to here, upon heat and using a distillation setup, basically distillation, the aldehyde only has dipole-dipole bonding, so it has a more moderate boiling point. It's the thing that boils out first. Your distillation shoves it down a condenser, and it basically collects it in a separate flask here, and that's going to be separated from our beginning primary alcohol and as well as our carboxylic acid. So this one here ends up forming our aldehyde. If you go all the way, if upon heat treatment and you just reflux it, if you just use that whole condenser again and you just continuously boil it, you don't let any of it escape, you're not collecting any of that middle product off, we end up getting a carboxylic acid. In tomorrow's lesson, we're going to see, since that is an oxidation reaction, you can actually use reducing agents and reduce them back into alcohol. More on that tomorrow. We're going to look at our alkyl halides. They undergo nucleophilic substitution. So alkyl halides, we saw hydroxyl, OH minus. Hydroxide is actually a good nucleophile group. It seeks out the polar positive end of the carbon. So this one here, we're going to start getting sort of cross combinations here. If I have a nucleophile and it replaces the X group on the halogen alkane, you end up forming an alcohol. So that's a sort of a combination there. We had other nucleophiles as well. One nucleophile here was to add a amine group or ammonia group here. This one here ended up forming an amine. Whenever I say amine or amino, amine, I think there's going to be some nitrogen present. If you have a cyano group around, so cyanide, this one here can end up forming a nitrile for you. So those are two other families that we've seen previous. So if you want to create those ones, at least we have a mechanism to do that. And then yesterday we started looking at condensation reactions. The tricky thing was it actually dealt with two organic groupings, so two of these bubbles here. What we did is we took the carboxylic acid. The carboxylic acid here has C double bond O single bond OH on the same carbon. If this one here were, for example, carbon double bond O and a carbon and then an OH, this one here is not a carboxylic acid. This one here would have a ketone possible functionality here and probably just an alcohol functionality, and we know sort of specific behaviors for each functional group. But this carboxylic acid here has the double bond O and the OH on the exact same carbon. We were able to match up the oxidized form of carboxylic acid with the alcohol group again. This one here ended up adding together to end up forming an ester. An ester is a C double bond O group like that. So that comes sort of mid-chain. We also found carboxylic acid with amines. So let's figure out where our amines were. Amines are way over here. So let's just use another color here. A carboxylic acid, if I react it, if I condense it with the amine, condensation reaction pulls off of water, releases off of water. That's when we ended up getting our amide. So yet another organic family. You see how, especially as you start drawing this mind map here, not only do you start memorizing some of these reacting conditions here, you see some of the interconversions between them. Okay, we'll keep practicing drawing this mind map, but tomorrow we're going to add the one last addition. Okay. In today's lesson here, we're going to switch over to take a look at benzene. Okay, benzene is a very common organic chemical here, C6H6. Benzene does something called resonance. So just before we look at the benzene's molecule entirely, let's just remind ourselves what we know about resonance. So let's just do, for argument's sake here, ethanoic acid. Whenever it's eth, it means that there's two carbons. The oic acid tells you there's a carboxylic acid. You should fairly easy be able to draw this one here. CH3C double bond O OH. I've been saying previous here, this OH here is the very same hydroxyl group that bases need to have. It's just that in water, this covalent bond here doesn't break. So you don't just have an OH and suddenly your base. You have to remember Arrhenius definition, Bronsted-Lowry definition. You have to be able to somehow get an OH in solution when you're dissolved. This compound here for carboxylic acids, the reason why they're acids is we actually refer to this H on the end. This one here is actually easily removable proton. Right? So not only if you just sort of compare bond enthalpies, you're going to find water has an easier time breaking off an O and H. One reason why we can predict for this, we know this one here from our acid-base chapter, this one here is a weak acid, so we know it ends up in equilibrium. It doesn't break off all that well, albeit this is the easiest to remove. The other H's don't come off. So we have our CH3 group still there, C double bond O. Why is that one so easily removable? When I pull it off, it ends up leaving as a H+, so it leaves behind its electron. So if I want to do an electron pushing arrow here, I just do both electrons go back on the oxygen. So therefore, I have this negative here. They always like testing this compound here. Basically, earlier, we had no resonance. Earlier, based on formal charges, the double bond here should just be for the oxygen. But now that I've removed the hydrogen, now it's a toss-up. Now it could be this guy double bonding, or we could actually be in resonance with another form of this one. What if the double bond were actually on this side? If you check the formal charges are going to be identical on both sides. The other one here, the single bonded oxygen, will relatively have that negative charge. So as a conclusion here, we have this notion of resonance. Resonance is this notion of delocalized electrons. Resonance, or having these delocalized electrons shared, helps add stability. And in organic here, if I have a mechanism and it ends up creating a compound that's more stable, that's going to be a more likely pathway. Although we've been trying to avoid in chapter 5, we're like, okay, if it's energetically stable, it doesn't necessarily mean fast. In this organic chapter, sometimes it does refer to, well, this compound here is stable. Not only is the pathway more likely, it does usually correspond with it being faster as well. But in general, I try to avoid that, oh, it's more stable, so it has to be fast. That's not necessarily true. For resonance here, so the two double bonds here that make up what would have been the pi bond can actually be shared over. We define something called the bond order. So it was a number to actually define, well, what is this bond, right? Neither of these resonance forms actually captures the real picture. I have three bonds trying to be split two ways. We have like a 1.5 bond order on both sides. So it's slightly stronger than a single bond, slightly shorter than a single bond as well, sort of like a 1.5 bond. It's like that sort of dragon. It can't really be captured by a dragon. Is sort of part lizard and part dinosaur, things like that. It's not constantly flipping between half the time it's lizard, half the time it's dragon. The dragon is just sitting there being the dragon. It's just we can't draw it, so we have to draw. Well, it sort of have characteristics of these ones. It's sort of some average between those ones here. So with that in mind here, let's take a look at benzene. Benzene actually is a different functionality here. This is actually going to put us in the aromatic family. The word aromatic means it actually is a smelly compound. Not necessarily it smells nice, but that was one thing it was definitely known for. Benzene, if you look at the formula, is C6H6. Now that, for starters here, is really surprising because if you just look at the general formula of an alkane, we always go back to this one, CnH2n plus 2, if we had C6, 2 times 6 is 12 plus 2, that's actually C6H14. So this one here is the fully saturated form. Evidently, having lost hydrogens, we've actually become unsaturated. The question here is, what did benzene do so that it is its own stable compound, and what did it do to actually lose a hydrogen? It actually has 4 degrees of unsaturation. And we're going to see this a little bit more in our side chapter on spectrochemical techniques, but we're going to find every time you take a single bond and you convert this into a double bond, a single bond was saturated, I can hold all sort of the 6 hydrogens that I wanted, but if I want to end up forming a double bond, I'm actually using 2 of my electrons just to do the double bond. That only leaves me 2 extra arms to hold hydrogen, so C2H4. So every time I form multiple bond, that's 1 degree of unsaturation. Every time a double bond switches to triple bond, again 1 degree of unsaturation. The other thing that could happen here is, let's say we ended up having a propane, so 3 carbons like this, that should be C3H8. If I want to end up forming a ring, I need to ditch the 2 hydrogens on the end and connect these ones, and therefore I end up getting cyclo. So every time I form a ring, for every ring, I also have 1 degree of unsaturation. I lose 2 hydrogens every time. So if you look at benzene structure here, it's actually done 4 things in total. It's formed a ring, that's 1 degree, and it's formed 3 other double bonds. Each time those single bonds convert to a double bond, I lost another 2 hydrogens, leaving you with this nice sort of turtle-like structure here. This one here, looking at the hybridization, every carbon center has the equivalent of 3 electron domains. So I know this right here is trigonoplanar, so I know it's flat, and I know the hybridization is actually sp2. So I have an s orbital and a p orbital like that. I've traded in 3 of them. Notice that all of these actually have an unhybridized p orbital. It's actually those unhybridized p orbitals that actually allow for benzene to have delocalization. So if you imagine just sort of looking at this benzene molecule here, let me even just draw it flat so it's a little bit easier to see. So most of the parts here is trigonoplanar at every single carbon center. So that's the flat ring here. All of them have a unhybridized p orbital. So I have p orbital. It wasn't traded in to do the mix. I have the equivalent of 3 double bonds. So if it really were a double bond, the electrons would stick between those carbons there and end up becoming a pi bond. But because of the delocalization, it didn't have to be the top left, right, and the bottom left here. It could have been, for example, the top right, the left, and this one here. These 2 structures are said to be in resonance. The electrons that end up forming these 3 double bonds here are effectively delocalized. We can say there's actually pi delocalization. It's like the pi bond has actually spread around the ring. Pi delocalization around the ring. Okay. So the drawing to the right here is not the true structure of benzene, right? This one here is only 1 resonance form. It really isn't a double single double single. That actually, this pattern of double single is actually referred to as a conjugation structure, conjugation system. Conjugation system is an alternating single and double. We're going to find in our energy option that actually allows for the delocalization to happen easier, and it ends up starting to absorb higher wavelengths. So some of these compounds here are actually colored. Turns out benzene ring does not have really a double bond and single double like that. Instead, it's 1.5 bond order all the way around. Because for every carbon, it has the equivalent of 1, 2, 3 bonds. Those are the ones that are holding the carbons together. 3 bonds split 2 ways. Again, the 1.5 bond order, somewhere between a single bond and a double bond. So typically benzene is represented here. We have a 6-carbon ring, and then we have the circle in the middle. That circle refers to the delocalization. Any electrons in these pi orbitals here can swim around the top or swim around the bottom there. There are the equivalent of 3 pi bonds there, but they are evenly shared between all the centers there. Okay. So what are some evidences for the structure of benzene here? The carbon-carbon bond lengths, when you actually measure it in detail here, that one there were all found to be equal, so that corresponds with our bond order being 1.5. Again, sometimes it's important for you to keep noting that this one here, the benzene here, is just it is a ring like that. Without me showing either the double bonds, so far it's just a cyclohexane, you have to at least have this O in the middle, and therefore that tells you it's actually a resonance. This is actually a combination of trying to draw it one way where it has alternating double, single, double like that. In resonance, we do this double-headed arrow, not equilibrium, but we do this one here as resonance with where the double ones could otherwise be as well. So the bond lengths themselves are actually found to be equal. Strangely, however, we already said this resonance here gives benzene actually a lot of stability. There was this sort of nature of science link here that the fellow that had actually discovered benzene structure, he actually discovered this via a dream. He had actually pictured, let's imagine we had a sort of 6-carbon parent, and let's imagine this was a snake, and then the snake ends up biting its tail. That ended up giving him this idea, oh, maybe it's ending up forming a ring, and then you get into a little bit of TOK stuff, like, okay, well, what's the validity if this came from interpreting a dream? I'll leave it for your TOK to study that part. As we started looking at reactions as well, benzene, curiously, benzene here is an alkene, right? And yet, let's think about the reactions that we know for alkenes. Alkenes are double bonds. It's a very electron-rich environment. That part there is usually a nucleophile. We usually add an electrophile across its double bond. And yet, benzene here experimentally, it doesn't undergo these addition reactions. Something's different from them. In fact, what ends up happening is benzene actually undergoes a substitution reaction and ends up trading one thing for another thing. So here's that note again with bromine water. So bromine water has Br2 in it. If I have a sample here that has just a regular old alkene, alkenes have C11C like that, because this bromine here is an electrophile here, this electron here can actually add the bromines across the double bond. This just occurs at room temperature, and we end up getting the 2 Brs just added across, forming that carbocation intermediate in the middle. Okay. Benzene doesn't do this. Benzene will not cause bromine to do this color change. Bromine converts itself from a reddish brownish liquid when it's actually a dihalogen alkene like this. This one is actually colorless. So that is a common experimental test for whether you have multiple bonds or not. Benzene actually doesn't do that. So it's a little bit weird. We're going to see what type of reaction that it does over the next slide or so. There's some other evidence that we want to know here. They always refer to this one. Imagine this one here is an energy level diagram. This one here is sort of a relative energy comparison. Remember, the lower energy actually means more stable. Right? So if it had a choice, I'd rather be lower energy here. What they're comparing here is starting off with just cyclohexane, right? So just having 6 carbons in a ring doesn't make me benzene. I have to have the full delocalization, the equivalent of 3 double bonds. What they've done is they've actually calculated here, all right, so what if we had just one single bond here? So one double bond. Benzene has the equivalent of 3. So what's going to happen here is when double bonds are hydrogenated, let's start off with this. When double bonds are hydrogenated, we saw that term before. It's not just a hydration, it's not just a reaction with water, it's adding a hydrogen across the double bond, energy is released. So imagine starting off with this theoretical molecule here. This is just a cyclohexene, right, with one double bond. That molecule can exist no problem. You would actually need to put in energy to rip apart that bond there. So as you put in energy here, this bond here ends up breaking. Overall, energy is released. Overall, this process here is exo. So if this one here ends up, even though you may need to trigger it, give it some activation energy to get it going, because this reaction is exothermic, this one gains 119 kilojoules per mole. That's going to be exothermic, so it drops. So it ends up forming cyclohexane. If I did the same sort of theoretical molecule, what if I had 3 of these bonds here? So if I have 3 of the double bonds here, again, every bond would require some energy to actually rip it off. This one here is exo, this one here is exo. Every time I hydrogenate it, I add the hydrogen across the double bond, I end up getting some energy back. This one ends up losing 357. And yet, when you actually compare the stability that we get for making this molecule, I have benzene. This one here also has the equivalence of 3 double bonds, but because this one here has resonance, it actually is a little bit more stable than we had talked about. So when we actually put in the energy, get the bonds to start breaking, we only gain 207 back. So from this diagram here, benzene is more stable than the expected, we're going to call it a triene molecule, so having 3 double bonds due to resonance stability, right, due to that delocalization of electrons. So now I know it's a little bit weird thinking about it this way. Like in some sense, I'm saying like, okay, here's the compound, and if I destroy the compound, then it becomes more stable. That's me looking at me putting energy in to rip apart the bonds. You can also say, well, going from cyclohexane, and then if I become benzene, having those 3 double bonds forming actually gives me 207 kilojoules per mole of stability. That's different from the expected triene molecule. As you start looking at the reactions for benzene here, recall that alkyl halides, so it was the polarity that actually caused you to do substitution reactions. It was a nucleophile that came in. Nucleophiles are very electron rich. They attack the positive end here. They cause a substitution. They cause the X group to leave, be it via an SN1 or SN2 mechanism. You have to know those ones. A halogenated benzene, so I have the benzene ring here. This benzene functionality is sometimes also referred to as a phenyl ring. So having a benzene C6H5, having this grouping here, that's referred to as a phenyl. It's in the aromatic family here. This part here is not easily hydrolyzed, so it's not easily substituted, just like our SN1, SN2, with even a strong nucleophile like OH minus for 3 reasons. Let me just list for you these 3 reasons. First one. Because of delocalized electrons, the carbon in the CX bond is less partial positive, right? So in the past, it used to be, well, here's the polarity, C and X like this. So we have the halogen group here, more electronegative. That side is partial negative, this side is partial positive. And yet what's happening here is, well, the carbon is actually experiencing some delocalization, some spreading out of negative density. That's actually going to decrease the positive polarity. That decreases the desire for a nucleophile to actually attack the carbon. That's one. Second is sort of a steric conversation here. The attack of carbon is blocked by the delocalized electrons. Okay, so this ring here, it forms fairly tight bonds here. You notice that the nucleophile has to actually work its way in between and actually attack this carbon here. There's not a lot of space to actually move around. So it's blocked by the delocalized electron. The nucleophile, we can be a little more specific here. The nucleophile, that is, nucleophile is repelled by the electron cloud, right, formed by the benzene ring. And sort of coupled to that reason here, the electrons on the X, let's write this down, so third reason, the electrons of the X, so of this group here, right, we already said it's going to be partial negative here. The electrons on X partially interact with the electrons on the ring, leading to a stronger CX bond. So remember when we were looking at these halides here, and we were saying, well, what does the speed depend on? In the one sense, we wanted the polarity here to be big. I want this to be really partial positive, so therefore my nucleophile has a desire to come in and actually attack it. And yet we found that as the polarity actually got more and more uneven, the C and F bond was actually the strongest. Experimentally, we actually found that the CI, it's actually more so the bond enthalpy that actually matters more. In this case here, they're saying the electrons on the end here and these electrons here end up making this bond here stronger than otherwise would be in other compounds there. So because of that, even though we do have a nucleophile like hydroxide is really, really strong, benzene derivatives here are not really easy to substitute. So finally, we're going to note if the halogen is not directly attached to the benzene ring, this one here can have really regular reactivity, so SN1, SN2. So we have this one here, we have our polar bond, so this would be C, it's bonded to two H's like this, and the halide. This time, this benzene is just a bulky side group here, no problem for a nucleophile to come in, let's use a different color. Our nucleophile here can come in from the side here and actually attack. Right? So that can happen, no problem, SN1, SN2. We're only talking if the halogen group is directly bonded to the phenyl ring itself. So just as an example here, we're going to have, let's say, a CH2Cl and a OH minus group. Right. So this one here, the halide that's going to be substituted is way off, so this is going to end up forming CH2OH and then Cl minus, no problem. Okay. I'm going to give you one quick aside here. Some of you, especially in your biology classes, may have learned about a molecule called diphenyl trichloroethane. This one here is usually shorthanded DDT. It was used as a pesticide some 60, 70 years ago. Really good in actually killing off unwanted insects, things like that. Unfortunately, it had the outcome of it was very toxic to some creatures that ended up ingesting it. The case study was for a lot of birds that actually, when this sort of built up in the system, when they would actually lay their eggs, when the DDT actually sort of got into their systems here, the DDT would actually cause thinning in the egg layer, so that when the bird went to sit on the egg, keep it warm and whatnot, we actually found that there was a lot of egg breaking because of the DDT. So egg thinning, and that was very devastating for a bird population, which is why since then this molecule here has been phased out. Just let me draw this picture for you here. So always good to think about the environment here. So it's going to be a dichloro, and the chloros are going to be added to phenyl rings. So phenyl are these benzene rings. So there's your dichlorodiphenyl, and then what we have is we have a carbon in the middle, and this one here is part of the ethane structure, and the ethane has a trichloroethane. So we have C, chlorine, chlorine, and chlorine. This one here is a carbocation here, so that part there susceptible to attack, so that's what made it so reactive there, but we had that sort of case study. Okay. We are going to look in a little bit more detail of what reactions benzene itself does. We said sort of what's the hardship in it doing substitutions SN1 and SN2 like other compounds, but we can see what reactions that it does. I'm just going to end off just taking a look at just this generic name here. So far, we've seen electrophilic addition, so alkenes. Alkenes have electrophilic addition across a double bond. So whether it's a halide or something that just adds across of it, no problem. For alkyl halides, our alkyl halides was the nucleophile was actually substituting. So this is actually nucleophilic substitution. That's where we got our words SN1, SN2 from. For benzene, this is our first example of actually an electrophilic substitution reaction. Okay. I'm going to leave this for the next lesson here, but just note that that's different. We've actually never seen a nucleophilic addition. If you go under organic chemistry, you can see it a little bit more. Okay. So I'll pick it up from here a little bit more tomorrow, and that should wrap up our organic chapter for us. Thanks, guys.